Hello students, welcome to our next video on Eigen decomposition, in which we will discuss special cases of symmetric matrices and learn about a very important theorem, what we call as the spectral theorem. And also we will solve one specific example, that how a eigen decomposition or diagonalization of a matrix looks like. So now this spectral decomposition is very important theorem when it comes to dealing with any kind of eigen decompositions, and it says that if a matrix A, which is a square matrix belonging to a real vector space and has dimensions of n cross n, it is symmetric, then there exists a orthonormal basis which will span the space V, and that would be of dimensions r cross n, r raised to power n. And the beauty of that ONB would be that it will comprise of the eigen vectors of A, and each eigen value of a square symmetric matrix would be real. Now what that guarantees? In last video, we learned that if we are given a square matrix n cross n, we can perform its decomposition in the form of PA, PD, P inverse, where this is a diagonal matrix and P has to be the basis of Rn. And spectral theorem just guarantees that if you are dealing with the square matrix, this P would always be the basis of Rn, and P would comprises of eigenvectors. So once you give us a matrix, we will quickly calculate its eigenvalues. From eigenvalues, we will calculate its eigenvectors, and that would ensure that that basis of Rn is known, and then we can easily decompose our A into its components, where D would be a diagonal matrix, making it much convenient for mathematics to work out. So let us look into one specific example, that how we can see that what these diagonal elements would look like. So if A is given to be 2, 1, 1, 2, you clearly see that this is symmetric. The first step would be the calculation of its eigenvalues, and eigenvalues can be simply calculated as determinant of A minus lambda I equal to 0, which can be written as determinant of 2 minus lambda, 1, 1. And when we solve it, we get lambda equal to 3 and lambda equal to 1. Now corresponding to lambda equal to 3 and lambda equal to 1, we will calculate their corresponding eigen spaces, or what we call as eigenvectors. So E3 and E1 can now be calculated as using the simple definition that AX equal to PX. So we will write 2, 1, 1, 2. P1 is the eigenvector corresponding to lambda equal to 1, and P2 is the eigenvector corresponding to lambda equal to 3. So we can write this as AX equal to PX. So simply I can write for lambda equal to 1 as 1 times P1, and when we solve it, we get P1 equal to 1 by root 2, 1 minus 1 after normalization. So mind it, this 1 by root 2 is coming from the fact that it can be divided by the square root, or the square root of the sum of squares, which becomes the norm, L2 norm. Similarly, P2 comes out to be 1 by root 2, 1, 1. If we replace this 1 by 3 and again solve this equation for P2, that would mean we can write our P matrix as 1 by root 2, 1 minus 1, 1, 1. And now you can clearly see that both these vectors, they are orthogonal, as if you take a dot product, it is going to come out to be 0. Also, the magnitude of individual vector is also equal to 1, because we have already normalized it by root 2. And hence, we can clearly say that since P is orthogonal, P inverse equal to P transpose, and we can write A as P D P inverse, or A equal to P D P transpose, which implies D can be written as P inverse AP, or D equal to P transpose AP. And we already know that this A is equal to 2, 1, 1, 2, and P transpose we can always calculate as 1, 1, minus 1, 1. This is 1 by root 2, and our P is given by 1, 1, minus 1, 1. And when we solve this, we would find that D in this case comes out to be 1, 3, 0, 0. Now, if you notice carefully, the elements along the diagonal of these D also happen to be eigenvalues. So as soon as we determine the eigenvalues for a square symmetric matrix, as soon as we determine the eigenvectors, we have actually decomposed our entire matrix as the basis that comprises of eigenvectors, a diagonalized matrix that comprises of eigenvalues, and the transpose of the matrix that consists of eigenvectors. And this is the beauty of dealing with square symmetric matrices. And once we determine eigenvalues and eigenvectors, we have totally decoded the characteristics associated with the square symmetric matrix. Also, in the literature, you will frequently encounter that many of scientists, they prefer to work with the covariance matrix. And when we will go into principal component analysis, we will realize the importance of covariance matrix. But these covariance matrix guarantees both of these conditions. If you recall from our time series discussion, we can write covariance matrices as sigma xx, sigma yy, sigma xy, sigma yx, and they are symmetric as well as they are square. And if we have to perform their eigen decomposition, we simply determine their eigenvalues, corresponding eigenvectors, and we can easily decompose them in the way we want. And each eigenvector associated with the eigenvalues arranged in descending orders give us the dominant modes. And when we talk about empirical orthogonal function or principal component analysis, we are always interested to identify what are the dominant modes in the data set that can explain a lot of variance or lot of variability, which would be our topic of discussion when we go towards the detailed analysis of principal component analysis. Thank you.